Noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
Okay, go ahead and take a deep breath. You probably don't think much about the empty air filling your lungs right now, do you? We tend to view oxygen as just this boring, invisible gas that happens to keep us alive. But what if I told you that molecular oxygen is actually a heavy, magnetic, shape-shifting powerhouse? Welcome to this explainer. Today we're going to completely dismantle your perception of dioxygen. We'll be exploring its hidden states, its volatile mutations, and its role as the ultimate biological engine.
Let's kick things off with a really simple question. What color is oxygen? Now, if you said colorless, well, yeah, you'd be right. But only right here at standard room temperature and pressure. That is just one tiny sliver of this molecule's reality. As you're about to see, when you start tweaking the temperature and the pressure, oxygen shatters the illusion of being this invisible nothingness and transforms into something entirely alien.
Here's the roadmap for our journey today. First, quantum secrets. Second, bizarre states. Third, high-tech storage. Fourth, extreme compounds. Fifth, the biological engine. And finally, number 6, essential but not enough.
All right, jumping into Section 1, Quantum Secrets of Oxygen.
To really understand oxygen, we have to look down at its natural triplet state. It actually has 2 unpaired electrons hanging out in its outermost orbitals. Because of these electrons, oxygen exhibits paramagnetism. Yep, it's literally magnetic. But even more importantly, those electrons act like a locked door. Or think of it like a bouncer at a club. The rules of quantum spin conservation create this massive kinetic barrier. Basically, without some sort of thermal activation or a catalyst, triplet oxygen cannot directly react with the singlet organic molecules that make up our bodies. This quantum bouncer is literally the only reason you don't spontaneously burst into flames just by taking a breath.
Moving right along to Section 2, Bizarre States and Phases.
So we know it's a magnetic gas with a chemical safety lock, but what happens when you drop the temperature down below 90 Kelvin? Well, oxygen condenses into a liquid, and it's not clear, it's pale blue. It's also strongly paramagnetic, meaning this blue liquid will literally stick to the poles of a powerful magnet. But wait, it gets crazier. If you compress it between 10 and 96 gigapascals, it forms the epsilon solid phase. It structurally collapses into clusters of 8 oxygen atoms, turning into these deep red crystals.
And if you push the pressure beyond that unimaginable threshold of 96 gigapascals, those red crystals collapse again into the zeta phase. At this extreme pressure, oxygen completely stops being an insulator and becomes a dense, interconnected metallic solid. It even exhibits low-temperature superconductivity. Just think about that. That empty air you are breathing right now has the potential to become a superconducting metal.
Now for Section 3, High-Tech Oxygen Storage.
Clearly, this is a seriously powerful molecule. So how do we tame it? Well, human engineering has figured out some truly fascinating ways to store and release large quantities of oxygen on demand. One of the most remarkable breakthroughs involves a unique double peroxide crystal called BaYMn₂O₅ plus delta. It works basically like a molecular sponge, driven by alternating layers of barium and yttrium. When fully oxygenated, it sits in an orthorhombic O6 phase. But when you lower the surrounding oxygen pressure, the crystal undergoes a phase transition to an intermediate O5.5 phase, and eventually down to a fully reduced tetragonal O5 phase. What's actually happening here is that the crystal is selectively emptying its yttrium planes of oxygen atoms, which perfectly traps and releases the gas.
To manufacture this material for peak efficiency, engineers use a wet chemical synthesis with an EDTA agent. This lowers the firing temperatures down to around 800 to 900 degrees Celsius, which creates fine powders with really high surface areas. The result of all this? Rapid redox kinetics. This crystal can reach oxygen equilibrium in just 10 to 20 minutes during gas switching cycles. That makes it incredibly useful for advanced tech like flameless hydrocarbon combustion and chemical looping.
Let's slide into Section 4, allotropes and extreme compounds.
We've seen how to store it, but what happens when we force oxygen into highly reactive configurations? Remember that bouncer at the club we talked about earlier? That spin-forbidden barrier? Well, singlet oxygen is what happens when you bypass security entirely. By pumping energy into the molecule, you pair up those valence electrons, and that removes the kinetic barrier completely. Singlet oxygen is an electrophilic oxidant that aggressively attacks organic molecules without needing any heat at all. Fortunately for us, it has a very short isolated lifespan, about 45 minutes as a gas and only microseconds in liquid.
Then we have dioxygenyl salts. This is oxygen forced into a positive charge. You get this by stripping away an electron using extreme oxidizers like platinum hexafluoride. When this happens, the bond between the oxygen atoms literally contracts and strengthens. But let me tell you, these salts are violently reactive. If they come into contact with even a tiny drop of moisture, they instantly hydrolyze, and that reaction releases oxygen, ozone, and highly corrosive hydrofluoric acid.
Consider trioxidane, or H2O3. It's an unstable, zigzag chain of 3 oxygen atoms. In organic solvents like acetone, it has a half-life of about 16 minutes. But look at what happens when it hits water. Water acts as a bifunctional catalyst here, and the molecule is just instantly obliterated. It decomposes into water and that aggressive singlet oxygen we just talked about in literally 20 milliseconds.
Which brings us to Section 5, the biological oxygen engine.
Now, biology takes this insanely potent, volatile chemical we've been discussing and somehow safely harnesses it. Inside us, oxygen acts as the terminal electron acceptor for aerobic respiration. Because it has such a ridiculously high reduction potential, an enzyme in our mitochondria called cytochrome C oxidase can safely perform a 4-electron reduction of oxygen into water. This brilliant mechanism avoids releasing those dangerous free radicals we just saw, all while generating a massive energy payload of 30 to 32 moles of ATP per mole of glucose. This right here is the energetic foundation for all complex multicellular life. But because oxygen is so dangerous and doesn't dissolve well in our bodily fluids, life actually had to invent cages to transport it, and different evolutionary paths solved this problem in their own unique ways. We vertebrates use hemoglobin, which grabs oxygen with an iron center in an end-on bent geometry. Arthropods, on the other hand, use hemocyanin, relying on copper for a side-on peroxo hold. And marine invertebrates use hemerythrin, which is an entirely different iron complex. It's biological engineering, perfectly adapted to safely carry a reactive payload.
And you know, none of this would be possible without a massive planetary shift. About 2.4 billion years ago, the Great Oxidation Event kicked off. Cyanobacteria started splitting water using solar energy, completely flooding the Earth's atmosphere with biogenic oxygen. This transformed our entire planet from a reducing state to an oxidizing state, which ultimately established the protective ozone layer that shields us from UV radiation today.
And finally, Section 6, essential but not enough.
We've seen just how incredibly powerful oxygen is, but it actually plays a very specific, almost philosophical role as a necessary but ultimately insufficient condition for complex systems. Look at biotic systems. Oxygen is structurally vital for complex life because of that huge ATP yield we talked about. Yet, for obligate anaerobes, it's incredibly toxic and causes instant metabolic shutdown. And importantly, oxygen alone cannot spark life. It needs liquid water, bioelements, and stable conditions. The exact same thing goes for the abiotic world. It's absolutely necessary for forming the silicate minerals in Earth's crust and for cleaning atmospheric methane, but it is entirely insufficient to drive geochemical transformations without external inputs like heat or UV radiation. To quote directly from the source material, without photosynthetic replenishment, atmospheric dioxygen would consume itself through reactions with surface rocks and organic sinks within millions of years. Earth's atmosphere is maintained at 21% oxygen through continuous, ongoing biological effort. It is effectively a slow,
planetary-scale chemical fire. Our atmosphere is in a constant state of chemical disequilibrium, and life is literally the only thing keeping that fire fueled.
And that brilliantly leads us to our final thought for today. If oxygen is a relentless oxidizer that destroys itself by reacting with rocks and organic matter and requires a massive planetary network of photosynthesis to maintain its presence, what does that mean for the empty skies of exoplanets? When astronomers look out at distant worlds and search for atmospheric oxygen, they aren't just looking for a gas, they are looking for a biosphere. So the next time you take a breath, remember, you aren't just inhaling a colorless gas. You're breathing a magnetic, shape-shifting biosignature that proves our planet is alive. Thanks so much for joining me on this explainer, and keep questioning what you think you know.
Like what you share.
This website makes learning so easy. I found all my resources here.
Noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.